I'd like to start out as usual with some review from last time and also maybe tie up a few loose ends that became apparent to me that should be addressed in last class. So I want to start with the thing that we ended with last time, which is correlation. So what is the idea behind defining a notion of correlation instead of just sticking with covariance, which after all is simpler, and just call it a day? Right off the bat, let's hear from someone. Nick has an answer here. Do you want to elaborate on this? Yeah, that's great. So I'll write it down here as well. So the main idea is that you want to account for scale in some way. So covariance depends on the units of the random variable or the scale of the random variable. So if you, let's say, change from feet to inches, which introduces an extra factor of 12, covariance is going to scale by that same factor. So you can't look at a covariance like 0.069 and say immediately some salient information about what that's telling you about the relationship between two random variables. The sign that it's positive, that tells you something, but the magnitude, the information contained in it is sort of muddled because it's got this information about the variance of the random variables baked into it. So we divide out by the variance, specifically divide out by the product of the standard deviations of the two random variables, and that takes us to an absolute scale so that we're between -1 and 1 no matter what the original random variables we're doing. So here's a mathlet to help visualize this. This is the same mathlet from last time, except that it registers correlation down here in the corner instead of covariance. So once again, you can move the masses around and you can sort of upset the balance here. You know, this is not the full range of flexibility you would have with 4 masses. I would need 3 sliders for that. So you could adjust 3 of the masses. The fourth would have to be 1 minus the sum of the other 3. But then you could really look at any four mass distribution. But anyway, this provides enough flexibility for what we're going to explore here. I'll give you a prompt so that you have something concrete to do with this mathlet and really learn from it. So the goal is to arrange the masses in the mathlet in such a way that the correlation is 1. I really love this, by the way. I can see what everyone's doing on their graph, and it really gives me some insight for how people are grappling with this, and also to some extent what knowledge you're bringing to the table here, and that's really useful for me. Okay, so the idea is going to be to position them along a line, and if you have a probability distribution that's concentrated along a particular line, then that distribution is going to have a correlation of 1. So here I put them all in a row, and it really doesn't matter how the masses are distributed. I can mix it all up. I can change, move this one way over here. We're still going to get a correlation of 1, no matter what I do with this. So being concentrated along a line is kind of what we're interested in when we're talking about correlation of 1, with one caveat that we'll come up against in a second. So I want to show a little bit why that's true algebraically. So maybe I'll get my whiteboard and try to sketch this. I'll also give you the formulas that we're going to get to here. So we need a little bit of algebra. I think the formula is just slightly too complicated to kind of hold everything in your head geometrically, but if you can kind of externalize that in algebraic notation, it really helps. So let's give ourselves a whiteboard and think about why it's the case that if you have points along a line, like let's just give ourselves these 3 points, why is it the case that the correlation is going to be 1? So it's pretty instructive to see. So the mean, let's say, is like here. Let's draw some lines to indicate where the mean is. And let's say that the line has a slope of k. And then I want to, instead of dealing with kind of too many variables here, I want to just describe the horizontal deviations. Let's call them D1, D2, and D3 of these 3 points. So when we're working out the correlation, remember that covariance divided by the product of the standard deviations. The covariance, if you remember from our exploration a couple of days ago, it's going to be horizontal deviation times vertical deviation for each of these points. So it's going to be like, for example, for this point, it's going to be D1 times the vertical deviation, and the slope of this line is k, so that's going to be k times d1. And we're ultimately going to need to average all of these contributions according to the probability masses. So if we call M1 the probability mass here at this point that we're considering, then the total contribution to the covariance of that point is going to be that mass times its horizontal deviation times the slope times the horizontal deviation again. So that's the contribution from just that particular point. And we're going to have similar contributions for the other 2 points. So we'll have M2 D2 K times D2 and M3 D3 K times D3, where M2 and M3 are the masses of the other 2 points. So all of this business gives us the covariance for these 3 points arrayed along a line. And we can do something similar for the variances. So we have the horizontal deviations and the probability masses. You can plug that in, very same idea here, except just with one variable instead of both x and y. And same idea with the vertical deviations. Those will all be, k times d1, k times d2, and k times d3. And you end up with this formula. So this formula looks like a bit of a mess, but it's really not that bad. So you can factor out a k in the top. You've got these k squareds here in all of these terms in this bottom factor, sort of bottom right factor. And then you can pull out those k squareds and then pull them out of the radical, and you get a k in the top, a k in the bottom. They cancel. And then everything else is actually the same. So the numerator works out to the same as the denominator. And so everything reduces to 1. So that's why I think it's not completely clear. You have to look at this a little bit, but I think it's helpful to see. Being along a line, it doesn't matter what the slope of the line is. The slope doesn't need to be 1 or any other particular thing. Being along a line is enough to give a correlation of 1. Except I've been eliding a kind of key point here that you might have already noticed from previous experience. So what happens if we array the points along a negative slope line? So we just did the algebra. It seems like it should be 1 again, because, where did we use that assumption? But if you do it in the figure, it's not. So what does a correlation actually work out? So you can use the mathlet if you want to figure that out. And what happened with this thing to give us a wrong answer? So we have a great answer here from Radhika. Do you want to explain what we did wrong here, Radhika? Excellent. So if we're being really careful, here's what's going on. We have a k in the numerator, a factor of k that comes out in the numerator. And then in the denominator, if we don't simplify it, we end up with square root of k squared. K divided by square root of k squared is not 1. It's actually equal to the sine of k, right? And that's for the reason Radhika just explained. If k is negative, then you end up with a negative value in top. And in the bottom, you have the absolute value of k, which is a positive number. So you end up with -1, since they have the same magnitude in top and bottom. So this part, the key point is that this is not k, it's absolute value of k. So anyway, it works out to the sine of the slope. That's what the correct formula is for the statements that I was making previously about if the probability masses are arrayed along a line, then the correlation is going to be 1. Actually, it's going to be equal to 1 if it's a positive slope line and -1 if it's a negative slope line. That's what we just worked out. Okay, here's another closely related question. Under what conditions is correlation undefined? So this you can't do with the mathlet, because if you move the masses around in the mathlet, it will always give you an answer. But there's a reason for that. In fact, it is possible mathematically to get an undefined correlation. What does it take for that to be true? Great, so I had several good answers here. Hardy, do you want to talk about what happens here if you have the masses arrayed along a vertical line? Yeah, that's a great point. So I was thinking of it more sort of directly in terms of this formula, but you're right, you can pull it back to that formula we just came up with. So, I wrote this down. This was also a bit of a lie, because in fact, if you're being careful, you're going to say this is the sine of k if K is non-zero, but it's not defined if K is zero. So, really, actually, instead of making this piecewise, I think the proper way to do it is to just qualify the whole statement, because like undefined is not really a value. So really what we need to do is just say if K is non-zero. If K is zero or infinity, so if you were talking about a vertical line, that kind of makes it really clear that there's a problem. But also there's a problem if K is zero, you'll have a horizontal line here. And then this expression works out to nonsense. Either way, there's a problem. You can see this directly in terms of the formula too, because you have sigma of x times sigma of y in the denominator. So if either one of those is zero, you're dividing by zero, you have a problem. So correlation is only defined when both random variables have positive variance. And a random variable has positive variance basically always, unless it's a constant random variable. So a random variable that returns the same value for every little omega and big omega. Usually we just think of that as a constant rather than as a random variable per se. But in any case, that's the only way to have zero variance. So any interesting random variable will have positive variance. So it's really only the kind of degenerate cases that give a problem here. And this makes sense. If you talk about correlations, like think about how you use it in the real world, there's a correlation between having a high vaccine rate and having a lower number of COVID deaths. That's something that you would never talk about where if one of the things doesn't vary. So if it's always the same forever, like what the correlation between COVID deaths in a state and whether it has oxygen in the air, it doesn't make sense. Every state has oxygen. There has to be actual variance in order to meaningfully talk about correlation on the kind of like common sense real world side. And that's mirrored here by having these zeros in the denominator. You learn math in school and your teacher's like, don't divide by zero. And you think, well, that kind of stinks. It's sort of a deficiency on math's part that it can't handle this basic operation that emerges from its basic rules. On the other hand, it's nice to have something in math that says this doesn't make sense, this is not defined, because there are instances in the real world where things don't make sense. We shouldn't be defining them for that reason. And if it manifests with a zero in the denominator, that's kind of satisfying. Let's move on to another topic, which is we're going to develop another formula for variance. So I want to do this because last time we did a little bit of manipulation of expressions involving expectation operators, and it seemed like folks were still very much getting used to that. So I want a little bit of practice, and this is a useful context of practice and a useful formula that we're going to arrive at. So what's the definition of variance that we gave last time? So the mathematical definition, if you have a random variable x, the variance of x is what? Okay, so lots of folks were close there, but this is I misread that. There's one thing missing here. Here we go. So this is one of the close answers. Actually, a few people had this answer. This is along the right line. So we're saying the random variable x minus its mean, like how far is the random variable from its mean, and let's square that. So, but this is still a random variable. If I give you a little omega, you can work out what is x of omega. The mean doesn't depend on little omega, but you can work that out based on knowledge of the whole random variable. And then subtract and square. That's going to give you something that does depend in general on little omega. This is a random variable. The variance should be a number. We're reducing x down to a single number. And this formula is the right one. So we do this thing. Sorry, there's just one missing parenthesis, but basically this is right. So we do this, and then that gives us a random variable, which says how far is this random variable in this particular roll of the dice from its mean. And then let's square that. So square distance from the mean. That's still a random variable. We want to take the expectation of that random variable. So that's the definition of variance. So simply put, definition of variance is the expectation of the square difference between the random variable and its mean. So you look at this expression and it's a little hard to read like this, like you're glancing at this formula and you almost have to parse all the brackets and parentheses right just to make sense of it. We really want to simplify this somewhat, and we'll see in a moment how it's helpful to have it simplified. But I think even already you can see like, okay, this is a little messy. But what's the thing we can do? You see this sort of algebraic expression and you're like, okay, well, I don't totally know where this is going, but I know one thing I can do. What is the one thing you look at that and you say, okay, well, I can do that for sure. Okay, so the idea is we have a value minus some other value and it's being squared. So that's definitely a thing we can write in a different way using some basic algebra. So here's what it looks like. We just square the first thing, we get that here. Then we'll have minus twice the product of these two things, and then plus the second thing squared. So this is just if you have a plus b squared, you square it out, a squared plus 2ab plus b squared. That's what this is. So no big deal there. Then what? What can we do now? You see this reflexively, you're like, well, I know a thing I can do with this. And there's kind of just one thing. Nice. So people are on the ball with this. That's great. Several good explanations. And Yoon Kyung is a couple steps ahead. So if you want to see where we're going, this answer kind of gets us all the way there. But let's break it down anyway. So we're going to distribute the expectation across the sum. Remember, we mentioned last time, we didn't prove this, but we mentioned last time and briefly the time before as well, that you can distribute expectation across addition always. You don't have to worry, are these random variables independent or otherwise well-behaved? It's totally irrelevant. Expectation distributes across addition all the time. It's just like an integral symbol, as we'll see in a bit. In fact, expectation just sort of is another manifestation of the same idea as integration, but it respects the same properties. So that can be kind of helpful to keep in mind if you have a lot of intuition built about how you can manipulate an integral symbol. In any case, we distribute expectation across here, and that's really all I did. I just copied this E symbol and put it in front of the three terms here. And well, this first term, there's nothing really we can do. Take the random variable, square it, take the expectation. How else could you write that? But these two, we still got some more work we can do. Expectation of 2 times x times, well, this is a constant. This is expectation of the mean squared. We can simplify some of this stuff. So we can simplify the middle term by pulling out the constant. So the mean of x is a number. You assess x holistically. What does it do on the whole probability space? Work out the probability weighted average of its values, and that's a number. So that does not depend on little omega. So we can just pull that out. Same thing with 2. 2 does not depend on little omega. We can pull that out. And so we get -2 times expectation of x. That's the one we pulled out. And then what we're left with is just an x on the inside. So this is where expectation of x comes in, this second one. It's this expectation operator, and then this is the only thing left after we pull out the other two things. So that's -2 times expectation of x times expectation of x. And in this last term, this is expectation of a constant. This doesn't even depend on omega. The whole thing doesn't depend on omega. So expectation of a just specific number just is that number. The average value of something that's always the same is that same thing. So what we're going to end up with here, as Yoon Kyung spelled out in her answer there, is expectation of x squared minus twice the square of the expectation plus the square of the expectation. So these are now the same algebraically. They're the same term, sort of variable wise. The only difference is the coefficients. You have -2 here. We have a +1 here. And that simplifies a little bit to expectation of x squared minus the square of the expectation of x. And this first term, just to give you a piece of terminology here, this first term is called the second moment of x. So the expectation of the square of x, that's also called the second moment. And the second term here is just the square of the mean. So we can say the variance of a random variable is its second moment minus the square of its mean. And this can be useful in lots of different ways. Just algebraically, when we're dealing with variances, we'll have fewer terms to think about. They'll be less entangled. That's nice. But also we can use it in a more indirect way. If we're wondering, sometimes you kind of forget, like, what does the expectation operator do and what does it not do? Like maybe you think, okay, maybe expectation commutes with squaring. I have expectation of x squared. Maybe I can pull that squared out if I want to. is that an algebraic operation I can perform, or is that invalid? So this formula actually gives us direct information about that. It says no. And why is that the case? So we had one answer come in, Nick. So tell us what you said here. Why is this true? Yeah, that's perfect. So if it were the case that squaring an expectation commuted, then every random variable would have a variance of 0. And of course, that doesn't make sense. In fact, we can produce an inequality here. We can say not only are they not the same, but since variance is non-negative, that tells us that the second moment is always greater than or equal to the square of the mean for any random variable, just by virtue of the fact that the variance of that random variable is non-negative. Okay, so I want to start working our way towards the law of large numbers, because we've talked about this idea that if you have a random variable that you can sample from, but the exact distribution of the random variable may be hard to access, you can approximate the average by sampling many times and just averaging those results, just a straight average. And that's going to give you, in the long run, if you have a large enough sample, it's going to give you a good approximation with a very high probability of the true mean. And that sort of feels like, if you're used to it, maybe it feels a little mundane. I think that there's something to be said for maintaining your sense of wonder about that. You have this completely random system, and all you do is sort of sample from its randomness repeatedly, and somehow that allows you to access information which is not random. Like you have a coin and you want to know, is it a fair coin? And you flip it 100,000 times, and somehow the probability of heads emerges from all of that chaotic randomness and kind of falls in your lap. It's there's something, I think, if it feels old hat, it's worth reflecting on a little bit more, because philosophically it's from a certain perspective kind of wild that you can have deterministic concrete information emerging from chaos, from randomness. But in any case, that's what happens, and we're going to see a little bit why that's the case here. So this is really kind of the rub. We'll jump straight in with the most important thing. So the goal is going to be to explain why the variance of a sum of independent random variables is equal to the sum of the variances. So we talked about this a little bit last time with 2 random variables. Now we're going to think about it with a whole bunch and see if you can come up with an explanation that convincingly persuades someone that this formula should be true. So only a couple of folks are typing on this one, so I want to break it down and make sure we're on the same page with this, because this is really, I think, the heart of the law of large numbers. So we have a bunch of random variables being added up, x1 to xn, and we want to compute their variance. So we just decided that a simple, convenient way to do that is square the random variable and take the expectation, and then also take the expectation and square it, subtract those things, and see where we end up. So let's do that. So our random variables are, our random variable, there's just one, but it happens to be the sum of a bunch of random variables. And what we need to do is square it and take the expectation. That's what we decided just a moment ago. And if you square a sum of a bunch of things, that's expectation of, I'll just do this geometrically, that's the area of this rectangle, or square, I should say, where the side lengths are x1, x2, and so on up to xn. So this is just, I could write this out algebraically and it would be fine, but I want to make it really vivid. So the area of this square is, well, definitely that's the same thing as this stuff squared, because that's what squaring means geometrically. And then we can split this into a sum of a bunch of areas. So this is going to be the expectation of, like, the area of this little piece down here. That's x1 squared plus this square here, x2 squared, and so on up to xn squared. That gets all of the diagonal parts of the square. Maybe I'll color this one orange and just go over this with orange. But then we have also all these other terms. So maybe I shouldn't have closed the bracket here. So x1, x2, That's this square. I'm running out of colors. So that's the gray square here and so on. So we can just fill in all of these. Every pairwise product of distinct x's is going to get its own term. All right, so you can just imagine all of those have been filled in. And now we can close the bracket. And now expectation distributes across this sum. So we're going to end up with just expectation of each one of these, x1 squared plus expectation of x2 squared, and so on, plus also all of the pairwise products. So I'll leave that there for now. I think looking at it in terms of this square up here is kind of the best way to keep it organized in your head rather than necessarily writing it algebraically. I write both here so you can build that correspondence in your mind, but ultimately this is what's going on. We want all these expectations of all the products. So that's just the first term though. That's this first part. And then we also need to do the second part, but the second part is really basically the same. It's just that we take the expectation first. So I'll clear all of this out. And we can say that for the second part, it's going to be expectation of x1 plus x2 and so on up to xn. And then all that is going to be squared later. So we're squaring afterwards here rather than before taking the expectation. And that means we can distribute the expectation and then square. And that's going to be the area of this same sort of rectangle, except instead of the side links being the values of the random variable, they're the expectations of the random variable because we already took the expectation. So expectation x1, expectation x2, and so on. Same thing in this direction. And so likewise, you're going to get all of these terms, all of the squared terms along the diagonal, all of the product terms along the off diagonal. And ultimately, it's going to be the same thing, except the expectation is going to be sort of right up on the random variable rather than being after the product happens. It's going to be the same formula as before, but the squaring happens later. So expectation of x1 squared, that's that very first rectangle down here, and so on. You're going to have similar terms for everything else. So I kind of wanted to walk through that and write it out so you can see sort of the steps and the thinking behind it. But it is easier to look at if I just give it to you in a pre-formatted message. So I'm just going to skip to that now. So this is what we just said. That first term works out to the sum of all these terms. These are just laying everything out in a grid. And the square of the expectation is the same idea, except expectation is going to be applied to each x rather than being applied after the product is taken. And so we can subtract these off, all of this stuff added together minus all of this stuff added together. But the thing is, it's easier to subtract them in pairs. You can say expectation of x1 squared minus the square of the expectation of x1. That will give us the contribution of this top left term. Same thing down the diagonal. That's just going to give us a bunch of copies of the variance of some random variables. This is the variance of x1. If we take this term minus this term, that's variance of x1. Second diagonal term is variance of x2, and so on all the way down the diagonal. And then off diagonal, expectation of x1, x2 is equal to expectation of x1 times expectation of x2 because the random variables are independent. We learned expectation distributes across the product if we know the random variables are independent. So that's what's going on. We just end up with, off from the diagonals, we get all of these terms on the right-hand side here, the variances of each random variable, and everything else is going to cancel. All the off-diagonal terms are going to cancel when we subtract. So this shows that the variance of a sum of independent random variables is equal to the sum of the variances. And this seems totally innocent. Like, how is that really going to help us solve anything? But actually, that's the key step. This is what makes law of large numbers really work. So let's take the sort of next step that follows on that key step. So suppose that x1, x2, and so on up to xn are independent random variables that all have the same distribution. So find the mean of the average of those n random variables. And for simplicity, you should express your answer in terms of the mean of one random variable. And customarily, people do this with x1. Great. So we had one answer come in. It's Yoon Kyung. So Yoon Kyung, do you want to tell us what happens here when we do this? Terrific. That was excellent. So you walked me right through that little write up. That's exactly what's going on. So we can distribute the expectation, pull out the factor of n in the denominator, and then we end up with a sum of a bunch of terms that are all the same. And so we can just say that's how many there are times what each one is, and then this factor of n cancels. So this makes sense if you think about it. You have some distribution and you sample from it a bunch of times and average the results. What is the average that you get for that new random variable? It should be the average of the original distribution. And this little piece of algebra indicates that that is actually the case. So yeah, that's exactly what's going on. There it is in my handwriting. Here it is in typeset form. Either way, you can see that the expectation of an average of some identically distributed random variables is just equal to the mean of each of those random variables. Now, what about variance? So I'll ask the same question again, find the but with variance instead of mean. So this is exactly the same question text. And this is actually just a little bit more thinking. It's a very similar progression to what we did last time. So you just need to think about how is variance different from expectation with respect to this derivation we just did. So a few people are typing up answers. I'll let folks finish doing that if they want to. And for everyone else, we can walk through this derivation. So I can almost just delete certain pieces here. Yeah, so if we drop out that expectation and replace it with the variance operator, and we can sort of just do that everywhere. So let me see. And it sort of seems like we're just going to end up with variance of x again, variance of x1, except there's one mistake here. There's one little thing that we have to do differently if we're talking about variance instead of expectation. So what's the one thing that we have to do differently here? So a couple of nice write-ups here. And we'll just extract the thing that happens. So when you pull out the n from a variance operator, so anytime you pull out a constant from a variance of some random variable, that constant needs to get squared when it comes out. So let's go back to this formula and change our pen color and correct what's going on. So we need a square right there. Whenever we pull a constant out, a variance operator, that constant gets squared. So then we have a squared here, and then that gives us a divided by n over there. So then we can delete this stuff and decide this is the right thing. And indeed, this is correct. So I'll share that in a message as well, so you don't have to read my handwriting if you don't want to. It's the same idea, but just with some sigmas and also its typeset. So the point is when you take a variance of a constant times a random variable, it's constant squared times that variance of that random variable. And this seems sort of, seems a little petty. It's like bookkeeping. Well, you're supposed to square it. Okay, let's square it. But actually having this extra factor of n in the bottom is really what makes it all go. So the point is that the mean is exactly the right thing. When you sample a bunch of times from the same distribution and you're trying to approximate the mean of that distribution, well, the new distribution that you come up with, the distribution of the average of many random variables, it has two really nice properties. Its mean is exactly in the right place. So if it's symmetric, it's going to be centered around exactly the point you're interested in. And it's unlikely to be far away from its mean because its variance is small. If it had a lot of probability mass far away from its mean, then just by the definition of variance, it would have a high variance. And it doesn't. It has a small variance if n is really large, because, well, whatever variance of x1 is, if n is a lot bigger than that, then this number is going to be small. And it's going to be very probable that the actual value of the random variable is quite close to its mean. So this is what you're doing when you do Monte Carlo simulation, you sample from a random variable a whole bunch of times and you average and you're like, I bet that's pretty close to the actual mean of this distribution. This is why it works. This little formula here combined with the same one, but for expectation, this is what makes it all go. So that's a good stopping point.